Hi everybody, welcome to another video in Business Calculus section 11.5 absolute maxima and minima. That plural of maximum and that is the plural of minimum. Right, first we define the absolute maximum and absolute minimum. So absolute maximum is the y values of the function that is bigger than everything else in the domain. And absolute minimum is the values of a function that is smaller than everything else in the domain, for every x in the domain of the function. So in this definition, we refer that to a y values. We can also refer to an absolute maximum point. In that case, we have the x values and the y values. But of course, a point is always x and the y values. The y values is the y value come from the original function. Right. Extreme value theorem. If the function that is continuous on the closed interval, then it has an absolute maximum and an absolute minimum in an interval. So we have two conditions. The function have to be continuous and the interval have to be closed. Then they have one absolute maximum and one absolute minimum values on the interval, right? So absolute values of the function. And they'll say why we have only one absolute maximum, one absolute minimum. Well, the reason we define this way is so we have a function from A to B. It goes like this. So they have the same highest y values, right? So there's one absolute maximum values that occurred at more than one values of x, but the y values, the highest values of y, there's only one. So that's why we define it to be an absolute maximum values of the function, right? Likewise, there are two points corresponding to the absolute minimum values. So that absolute minimum point, but the y values of those points will be the same. And unlike local max and local min, we compare the y values of the whole interval. We're not comparing to the point around it. Right. To summary, we define absolute maximum or absolute minimum values is the y values that is highest for every x in the domain or lowest for every x in the domain. And to guarantee we have an absolute maximum and an absolute minimum is the interval have to be closed and the function has to be continuous. Right, let's delve more into that. Say if we have the function going like this, there is the absolute minimum right here. There could be an absolute maximum there, but the point is not defined there. So because the interval is not closed, it is open at A, there may or may not be a maximum. In this case, there may not be a maximum. If it go like this, then yes, there is an absolute maximum. But if it go like this, the maximum does not exist on the boundary. So to guarantee that, we make it so that the boundary is closed. So it will have the endpoint if we need to. Right, so that's why we require the interval to be closed. The function have to be continuous. Well, that's easy. If we have from A to B and the function not continuous, and it go like that, so there's no maximum because the function just keep getting bigger and bigger, and there's no minimum because the function keep getting smaller. So this continuity will not guarantee to have a maximum or a minimum. So that's why we require the function to be continuous and the interval has to be closed. With that, we guarantee to have one maximum and one minimum values. One maximum values and one minimum values. And it might occur at more than one point, but the term of the values, there's only one. Alright, and to find it, right, that's what we said here. The absolute maximum absolute minimum will occur at the critical values or at the endpoint. So that's why we need endpoint, so the interval must be closed. Alright, the steps to find absolute maximum and absolute minimum. Make sure the function is continuous and then find the critical values. The function continuous on the closed interval, so we have the endpoints and we find the critical values, and then the absolute maximum and absolute minimum must occur at the critical values or at the endpoint. So we just check to see which one has the highest values of all the critical values and the boundary. Alright, so pretty straightforward. The function, check to make sure the function is continuous and the interval. So this is polynomial, so it's continuous everywhere. I'm just skip that step. The first step we do is just find the critical values. And critical values must be on the open interval a and b. In this case, -6 and 2. Right. So that is the function. We take the derivative. And that gives us 3x squared plus 6x minus 9. And then just like what we have been doing, equal to 0 does not exist. And this is a polynomial continuous everywhere, so it is defined everywhere, so we don't have anything that is undefined. Right, we divide everything by 3. So x squared plus 2x minus 3 equal to 0. I'm just going to use quadratic formula here, even though I can factor that one easily. Over 2a. Right. So that gives us -2 plus or minus 2 squares 4 plus 12, that's 16 over 2. So -2 plus or minus 4 over 2 minus 2 plus 4 over 2. 4 minus 2 is 2 over 2 is 1. Minus 2 negative minus 4 over 2, that's -3. So we have 1 and -3. Well, 1 and -3 belongs to the interval here. So yes, we check. So remember, back in the previous section when we trying to find critical values, we have to put this back into the original function and find the values. On this one, we do not need to do that because later on we will find the values at those points anyway. So we don't need to do that here. But first we check the function that is continuous on the interval. So that's good. And now these points are on that interval. So that's good. So we should check. We write, here's a note here. Both x equal to 1 and x equal to -3 are on the interval of -6 and 2. Notice that we don't need to be a closed interval here. Right, so that the second step, or usually the first step we do. The second one is evaluate the function and determine the maximum and minimum. So we have here, we have the absolute extrema must be at the critical values or at the endpoint. So those are the candidates for the maximum and minimum. So we're going to evaluate the function at those points and the function at the boundaries. So the second step, we just said we use a table. And the table using original function. Because we compare the values of the original function, so we can have the maximum or the minimum. So the function x cubed plus 3x squared minus 9x minus 7. The boundary -6 and -2. -6 and 2, sorry. And the critical values inside is -3 and 1. Right, put all of those values into the function, and then we determine the maximum and the minimum from there. Right, I enter the function in first. It's y equal to x cubed plus 3x squared minus 9x minus 7. Right, and then just go to table because those are whole numbers. So we just look at -6, that's -61, -3, that's 20, (1) is -12, and 2 is -5. Right. So based on this, obviously the biggest values is the max and the smallest values is the mean. So this is the absolute max, absolute maximum values, and this is absolute minimum values. So we say absolute max equal to 20 happen at x equal to -3, and absolute mean equal to -61 happen at x equal to -6. Right, check the function x cubed plus 2x squared minus 9x minus 7. Right, so just like that. Right, so we need the function to be continuous, the interval to be closed, and with that we find the critical point inside and the boundary. Put everything on the table. The biggest one is the max, the smallest one is the mean. Now we switch gear a little bit to the local extrema. And then you say, why do we do that? Well, it takes a while when we get to the point, but now it just go to the second derivative test and extrema. This is for the local extrema. Right, let's see big critical values. Well, that the first, it has to be a critical values. And if the second derivative greater than 0 or second derivative less than 0, the function concave up and concave down. We know that. But if it's concave up, where the second derivative being positive, if it go like this, and the point will have to be the mean. If it concave down, then there will be a maximum. And if it is equal to 0, it's inconclusive. Well, I just can draw that too. It's inconclusive, so we don't know. Kind of a surprise face. Right, so, but I have to be a critical values first. Again, this is only for the local extrema, not the absolute extrema. Absolute extrema, we did like we did before. Find critical values inside and the boundary, and that's all of them on the table. We're not doing the sign chart. Alright, so find the local extrema and maxima local extrema for the following function using the second derivative test. So first we have to find the critical values. Right, so for critical values, and we take derivative. Okay, 3x squared minus 12x plus 9. Right, critical values equal to 0 does not exist. But that first derivative, sorry. But this is a second derivative test, so more likely we will have to have the first derivative. So we can take the second derivative. If the first derivative does not exist, we cannot use the second derivative test, because the second derivative test, the second derivative does not exist if the first one does not exist at the point. Alright, now equal to 0, 3x squared minus 12x plus 9 equal to 0. By the way, like I said, the derivative is continuous everywhere, so it's defined everywhere. So we don't have anything that make it does not exist. Alright, divide everything by 3. So x squared minus 4x plus 3 equal to 0. Right, let's use quadratic formula. Negative b plus or minus b squared minus 4ac over 2a. That gives us 4 plus or minus 16 minus 12. 16 minus 12 is 4. Square root of 4 is 2. Divide by 2. So I have 4 plus 2 divided by 2. That's 6 divided by 2 is 3. 4 minus 2 divided by 2. That 2 divided by 2 is 1. So I have 3 and 1. Right? Right. Now, of course, we can find the values later, but let's say we just have that. Then we can, because the derivative is defined everywhere, and the function is defined everywhere too, so those certainly will give us the critical numbers, meaning when you put in the original function it will define. We may find it now or later, it doesn't matter, but now let's just go to the second derivative test. Of course, we find the second derivative. Give us 6x minus 12. And now the second derivative test, evaluate at x equal to 1. The second derivative at 1 equal to 6 times 1 minus 12. That's negative 6. And that's less than 0. Would open down. But that concave down, so that's an local maximum at negative 6. So concave down, so local maximum at x equal to negative 6. Right now we test at 3. Put 3 in for x on the second derivative. This is equal to 6, which is positive. Positive. The function concave up, and there will be a minimum. So we say local minimum at x equal to 6. Right, so we say absolute maximum, local maximum as -6 and local minimum at 6. If we want to find the values, we just make a little table here. That is the original function. And I said we could have checked it right after we found the points. Sorry, at 1 and 3, and write that clearly, so don't make that mistake. Clearly we say x equal to 1 and x equal to 3. Maximum at x equal to 1, minimum x equal to 3. Sorry. Right, now we put that in the original function, because absolute maximum or minimum are points, and points are from the original function. So x cubed minus 6x squared plus 9x plus 1. Right, we go to table for 1 and 3. We have 5 and 1. So from there we can say local max equal to something at x equal to 1. And at x equal to 1, the function equal to 5. Right? Local min equal to something at x equal to 3. At x equal to 3, y equal to 1. So that is our answer. Yeah. So the second derivative is nice because we don't have to construct the table. We just test upon. The problem is make sure we can check the derivative of the function easily. So that we use second derivative test if the second derivative is convenient to find. If the second derivative is too complicated to find, we're just going to use the first derivative test, which is used in the table. If it go like this, that's the minimum. If it go like this, that's the maximum. That is the first derivative test. Right. The second derivative test, there's a few things. It is inconclusive, so it could be anything. So there's a limit. The test is kind of limited in that sense, and also we require the second derivative to be to exist, and so we don't have the case to test where the first derivative does not exist. Right, now we have second this function. Again, we do the same thing. Find the critical values. We'll take the derivative. Take down to 6, we have 6 times 1, 6, which is x to the 5th. Take down to 5, minus 20, x to the 4th, and plus 100, x cubed. Right, equal to 0, does not exist. Which in this case we don't have anything, because that is continuous everywhere, therefore define everywhere. Alright, x to the 5th minus 20x to the 4th plus 100 x cubed equal to 0. We can factor out x cubed, and then we have x squared minus 20x to the fourth plus 100. I mean, factor out x cubed, so that's just to 20x plus 100 equal to 0. Right, so x cubed and that, so we will let x cubed equal to 0, and then x squared minus 20x plus 100 equal to 0. So that gives us x equal to 0, and this one I can use quadratic formula again. Negative b plus or minus b squared minus 4ac over 2a. Right, now focus here. 20 square, that 400. And that, so that's just 0, so x equal to 20 plus or minus 400 minus 400, so 0. So we only have one, that is 10. Right. Next, we construct a table. I mean the second derivative test. So 0 and 10, right? So the second derivative from the derivative function derivative. Now we take derivative again, 5x to the fourth minus 80x cubed plus 300 x squared. Right. We evaluate at x equal to 0. Now this one obvious. Put 0 in here. Everything is 0. Well, 0 is inconclusive, so we don't know if it is a maximum or minimum or could be neither. We'll just say inconclusive. And that is the limited part of the second derivative test. Sometimes it just gives you inconclusive when it equal to 0. Now we use 10. Right, just going to use this. 10 store to x. And do this minus 80x cubed plus 300x square. That also 0. That also inconclusive. Right? So when second derivative is equal to 0, it's inconclusive. Now, if we use the second derivative, that just doesn't work. We have to use the first derivative test. But let's just graph the function, see what happened. 1 divided by 6, x to the 6th power minus 4x to the 5th plus 25x squared, x to the 4th, sorry. Right, let's zoom out. So we can see at 0, that is the minimum, and at 10, look like this inconclusive there. But like that, the second derivative test is inconclusive when the second derivative equal to 0. So we're just going to stop there. We cannot say if it's the maximum or the minimum. Next, for this function, use the second derivative test to test the following points. Right, notice that these set points, this may or may not be the critical values. If we use a second derivative test, we require it to be the critical values, which those points may or may not be. So we have to check it first. So since we use a second derivative test, that means we have to use the first derivative. Anyway, so we find the first derivative. That will be 10x to the 4th minus 20 x cubed, and then we find the second derivative, 40x cubed minus 60x squared. Right, now let's test the points. At x equal to 0, we do need to test for the derivative though. I put 0 in the derivative. And it is equal to 0. So why do we need to do that? Well, we need to do that so we can say that x equal to 0 is a critical value, is a critical number. And then we can go to the second derivative test. Only then. Put 0 in the second derivative. Well, second derivative equal to 0, so that is inconclusive. Right, that's the first point. Next we go to second point, x equal to 1. So we need to put 1 into the derivative. 10 1 to the 4th minus 20 times 1 cubed. That gives us 10 minus 20, that's negative 10. So this is not equal to 0. Derivative is not equal to 0. So x equal to 1 is not a critical value. So we're just going to stop there. Because if it's not critical value, we cannot go ahead and use a second derivative. So x equal to 1 is not even the critical values. Now we test for x equal to 2. Again, put in the derivative. So 2 to the 4, 16 times 10, 160. 20 times 8, also 160. So that check. So that means x equal to 2 is a critical value. Then we can use the second derivative. Put 2 in the second derivative. I have to say 2 store into x. And now type that 40x cubed minus 60x squared. And that is 80. Positive, that means concave up. So we have the local minimum occur at x equal to 2. Right. So once again, this is simple to show that it has to be critical values. So that's why we find derivative and check it equal to 0 or not. If it's not, then it's not even the critical values. So it cannot be local max or local mean. Right? By the way, this one, the points are given. We just test the point. Right now, second derivative test for an absolute extrema, or this is called the critical point theorem. It says that if f is a continuous function on the interval with only one critical value. Now, the most important in this theorem is we only have one critical value in the interval. And then if the derivative equal to 0, so that means there are critical values. Second derivative is positive. That the absolute minimum. Second derivative is negative. Absolute maximum. So there's nothing. Of course, open up there's mean, open down there's a max. So that's no big deal here. But the thing is, the most important, if we write that differently, we can say it, when I have only one critical value, then the local minimum is also an absolute minimum, and local maximum is also absolute maximum. Now think about this. If we only have one critical value and it goes down and up, that guaranteed to be the minimum. And this is not only the local minimum, it is absolute minimum because it is lower than those points. Everything else. Now, this we have only one critical value, so it have to be on the highest. It will be higher than the right and the left. So in this case, we have the absolute maximum also occur at the local maximum. Right. So why is that important? Well, we see that in the next two examples. Find the absolute extrema on the interval 0 to infinity. So at first, when we look at this, what is the problem with it? Well, we see the problem with this is we have the theorem that said if the function is continuous and the interval is closed, then we guarantee to have an absolute maximum and an absolute minimum. This interval is not closed, so we may or may not have the maximum, or we may or may not have the minimum, because that theorem does not have all the requirements. Right, but regardless, we still need to find critical values. So we take the derivative, which is 1. By the way, I can rewrite this as x plus 4x to negative 1. Right. Derivative of x is 1. Derivative of this is minus 4x to negative 2. If we rewrite and multiply x squared top and bottom for the common denominator. Right, equal to 0, the analysis, that's what we have been doing, right? So x squared minus 4 equal to 0. We have x squared equal to 4. Don't forget that if we take the square root on both sides, there should be a plus or minus. And does not exist when the bottom equal to 0. Right. So equal to 0 meaning the top is 0. We talk about that. Does not exist meaning the bottom is 0. So you have 0 and plus or minus 2. Right. Remember, this problem we're supposed to find an absolute extremum on the interval. Right, now on the interval of 0 and infinity, there's a 2, and that's only 2. The negative 2 is not in there, the 0 is not in there. So we say on the interval there is only one critical values of x equal to 2. That means we can use this theorem. So we'll find a second derivative from here. Derivative of 1 is 0. Derivative of this is positive 8 x to negative 3, or 8 over x cubed. Evaluate at 2. And the second derivative is positive, meaning it is concave up. So we have the local minimum at x equal to 2. Local minimum at x equal to 2. Now, according to the theorem, if we have exactly one critical values, it's not only the local mean, it is also absolute mean equal to at x equal to 2. We know it is at x equal to 2. So, because it is only one critical values, we can say the local mean is also absolute mean, local max is also absolute max. And if we put 2 in the original function, 2 plus 4 over 2, so 2 plus 2 is 4. So you have the absolute minimum is equal to 4 at x equal to 2, and there is no absolute maximum. Right? Because we only have one critical values, and we don't have the boundary, so we cannot really find anything else. Right? So that's what this theorem is about. If there is only one critical values on the interval, then if whatever it is, if it is local max, it will be absolute max. If it is a local mean, it will be absolute mean. Now in case of this problem, how do we know that it is no absolute max? Well, we know it goes from 0 to infinity. If x go to 0, putting 0 here, we have 0 and 4 over 0. It's going to be on the positive side, so that's going to be infinity. When x go to infinity, x plus 4 over x. Now infinity plus 4 over infinity, which go to 0. So that equal to infinity. So in this problem, when x go to 0 on the right side, it go to infinity. When x go to infinity, it go to infinity. So we have the function like this. And with 2, there's a local minimum there. On the left side, it go to infinity. On the right side, go to infinity. So that's why there's no maximum here, because it just keep getting higher and higher. Right. So, but the point of this problem is we find critical values, and just happen that it is the only critical values then we just use the second derivative test and to confirm that it is local mean. If it is local mean, it will be absolute mean. If it is a local max, it will be absolute max. And we have another example here. Find the absolute extrema on 0 to infinity. Right. First of all, of course, find critical point on that interval. Just one of the last one. Find critical point, critical values on the interval. Right, derivative. Of this one derivative, I have to use the chain rule. Something square is going to be 2 times that thing and derivative of it. I just happen to have ln of x inside of it. And then derivative of ln of x is 1 over x. So we have 2 times ln of x. Derivative of ln of x is 1 over x minus 3 over x. So we have common denominator of x. The top I have 2 ln of x minus 3. Right, equal to 0, does not exist. Meaning the top is 0. Does not exist where the bottom equals 0, 0. The top equal to 0. The bottom equal to 0. This one gives us just x equal to 0. Now we solve for x. So for ln of x, plus 3 on both sides, and divide by 2. And to get rid of the ln, we will raise both sides to the e power. So if x equal to e to the 3/2. To get the estimate values. 4.48. Right, now the critical values on 0 to infinity, there's only one. So we make an observation that on the interval of 0 to infinity, there is only one critical value. So we're going to test to see if this one the maximum or the minimum. Well, if we use the second derivative test, we have to use the second derivative. Well, in this case, why don't we use the first derivative test, which is the sign chart. Of course, we can use the second derivative test also, but I just said we can use the first derivative test as well. Sorry, on this problem, we only go from 0 to infinity. And inside there's only one point, e to the 3/2, which is about 4.48. And the derivative, 2 ln x minus 3 over x. And that when when x equal to e to 3/2, the derivative equal to 0. Right, test point 1 and let's say 5. Just put in the function, not really function, the derivative, sorry, alpha y equal, we have fraction 2 ln of x minus 3 and over x. Let's go to table. At 1 it is negative, at 5 it is positive, so the function goes like this. Now if the function goes like this, it's guaranteed to be a local maximum here, and not only local maximum, it is absolute maximum because there's only one critical values, right? So we can use the second or the first derivative test, because the first or second derivative test will give us the local maximum or local minimum. If there's only one critical values, that local maximum or local minimum will also be the absolute maximum or absolute minimum, right? So here we have local max, so we say local max, and therefore absolute max at x equal to 3/2, e to the 3/2, sorry. Right now we can evaluate let's say e to the 3/2 store to x, store to x, and then we have the function of ln of x squared minus 3 ln of x, and we have negative 2.25. That is the values of the function. So I'm just going to say it here, original function f of e to the 3/2 is equal to 2.25, negative 2.25. So the conclusion is absolute maximum equal to negative 2.25 at x equal to e to the 3/2. And if we go like this, especially to infinity, there will be no local minimum because just keep going down. Right, so this section we find the absolute maximum and absolute minimum. First we will find the critical point, critical values inside the interval, and we just put in the table and test them. The biggest one is the max, the smallest one is the mean. That's straightforward, just that. We will look at the application for the absolute max, absolute mean in the next section. Right. Next we have the critical point theorem. We still find the absolute max and absolute mean here, but it says that if there's only one critical values in the interval, we can just use local max is absolute max, local mean is absolute mean, if there is only one critical values. Now that is extremely helpful when we don't have the closed boundary or we don't have a closed interval. Then use the critical point theorem is very important. So every time we have just one critical values, we can use the first derivative test or the second derivative test. If it is local mean, it will be absolute mean. If it is local max, it will be absolute max. So that's why this theorem is very important. But if we have more than one point, well, we cannot use second derivative test. We cannot use the first derivative test either. So if we have more than one critical values on the interval, this is the only way to do that. Put everything on the table. The biggest one is the max, the smallest one is the mean, right? Once again, if there's more than one critical values, this is the only way to find absolute max and absolute mean. Right. So with that, we finish section 11.5 here. As always, thank you for watching and see you in another video in Business Calculus.